we will continue our discussion on Woodward-Fieser rules for dienes, dinones, ketones, etc. And I had explained to you yesterday that the Woodward-Fieser rules basically describe where a base peak has to be found, can be decided, and then all other functional groups including conjugated dienes etc. contribute to the shifting of the lambda max, and we can estimate where the UV visible peak can appear. So, these are the basic rules, like just to remind you that butadiene or etc. Conjugated dienes 217 and 250, homoannular diene is 253, like that, the base peak etc. We were trying to do couple of examples. This is a conjugated diene, double bond, single bond, double bond, double bond, single bond, double bond, single bond, etc. And then we had I had explained to you how we can estimate the lambda max which corresponds to what type of transition. So, for example, whether it is n to pi star or pi to pi star, depending upon the intensity of the transition as well as the wavelength. So, based on that I had explained to you that we can estimate. Now, this is the simplest example, 1,4-benzodiene. The structure is here and parent diene is 2 and 4. There are 4 into 5 alkyl substituents. Exocyclic double bond is 2 into 5. So, the lambda max expected is 244 nanometer and observed is 247 nanometers. So, you can see how closely we come to the prediction of the wavelengths. In general, I have to tell you that there will not be much difference between the absorption peak if the lambda max is 244 and observed is 247, it comes within the experimental error purview. So, plus or minus 3 nanometers we can always expect depending upon the instrument. So, that is the kind of thing. Now, I want you to look at the next example, that is this compound. You can see that this compound has got 3 cyclohexane rings and there are 2 double bonds and one double bond outside the ring, 2 double bonds inside the ring, and there is one alkyl substituent somewhere here. So, what do is when we want to calculate where the lambda max is, we take a base value of 253 because it is known because it is a homoannular diene. What do we mean by homoannular? There are 2 conjugated double bond system is located inside a ring. So, this is double bond, single bond, double bond, and all these are inside the ring. So, we take it that the base peak should be at 253 nanometers. Now, you can calculate the ring residue. This is 1, this is 1 residue, this is second residue, this is third substituent, and fourth substituent and fifth substituent. All the bonds attached to double bond are you can take it as ring residue. Okay. So, you can see that for the if I start from the left, I can see inside the ring there is 1, 2 and then 3, and then 4, this is 5. 5 alkyl substituents are there, ring residues. So, actually these are ring residues, and alkyl substituent means there will be one CH3 group or something like that. So, we know that alkyl substituent adds about 5 nanometers to the base peak. So, this is contributes 25 nanometers, and then you can see that this double bond on the top of the two rings is attached to a ring inside in the middle. So, this double bond is known as exocyclic double bond. So, an exocyclic double bond, this double bond is exocyclic to this ring, and this double bond is exocyclic to this ring, and this double bond is exocyclic to top ring. So, ring at double bonds attached outside the rings, there are 3. So, 3 each exocyclic bond contributes about 5 nanometers, that is 15. So, there is also one extended double bond, because this is homoannular, then single bond and double bond attached extending the conjugation. So, extended double bond contributes about 30 nanometers. So, lambda max is, if you add up all this, the lambda max is 323 nanometer, where we should get a peak. And what is the observed value? Observed value is 320 nanometers. Again, you can see the closeness of the prediction, how accurate the empirical rules work in the ultraviolet region. Now, look at this example. This is known as 4-cyclohexenyl 2-pentene. So, I want you to find out where is the expected peak. Now, here you can see that it is the cyclohexenyl ring, it is not a benzene ring. So, the structure diene, this is a diene structure, double bond, single bond, double bond, single bond, and then there are substituents all over. So, if I start from here, the single bond 1 CH3, and then there is CH double bond, and then on the second carbon atom, third carbon atom, there is 1 CH3 and another double bond attached to a ring. So, this is a 2,4 diene system. So, it may be 1,3 diene or it may be 2,4 diene, either way we get conjugation. For example, this double bond can be here, this double then this becomes single bond, this becomes double bond, this becomes single bond. It would be one of the resonance structures. So, if I take this compound and try to determine where it is, the base value is 217, it is not 253, because both double bonds are not inside a ring, a 6 membered ring or 5 membered ring, carbon rings, it is not there. Base value is 217. There are 2 ring residues, one is this and another is this. So, 2 alkyl substituents are there, 1, 2. So, that is 2 that is 5, 10 and 2 ring residues, that is another 10, 1 exocyclic double bond attached to this ring, that is, if you add up all this, then it will be 242 nanometers and observed value is 242 nanometer, matching exactly what we are observing. So, now you look at this compound like this. Now, these are all, I want to tell you that most of the compounds what we are dealing with here in this class is are the natural products derived from bark of the trees or flowers or fruits or medicinal trees or something like that. So, these are all something like very fragrant compounds, tasty compounds, sometimes acids, lemon, etc. They all have, these are all natural products. So, the structure has to be determined. Quite often whenever we extract something, the structure needs to be determined, and if the structure needs to be determined, we want to know where the bonds are, etc. And once the structure is determined, we can expect where the peak is there. So, for this compound, the lambda max base value is 253, because I see a double bond here inside a ring. This is the conjugation system, double bond, single bond, double bond, and then single bond, double bond, and then single bond, single bond. So, this double bond is not in conjugation with the system. So, the only thing we are considering is a double bond in this structure. Here I see a homoannular diene, 2 double bonds inside one ring. So, here it is not, even though they are inside one ring, but they are separated by 2 single bonds. So, I cannot take it as an extended double bond or homoannular diene. But as far as this ring is concerned, it is a homoannular diene, base value is 253. So, there are extended double bonds. So, 2 extended double bonds are there. So, obviously it is 60, 5 ring residues 25 nanometers, 1 exocyclic double bond 5 nanometers, and calculated value and observed values are matching almost perfectly to 343 and 345. Here I think I have made a mistake. This double bond should have been here. Actually it is there is a typographical error. So, here that is why I have taken 2 extended double bonds instead of 1 extended double bond, as I had explained to you earlier. So, the typographical error, if you correct it, the double bond should be here in conjugation with this single double bond, double bond. So, let us look at another example. This is the compound. Here it is a 5 membered ring, and then double bond, double bond, single bond, and double bond, double bond, but we cannot take this as a conjugated diene, but as a conjugated ketone. So, this is cyclopentanone system, parent value is 202. If you look at the rules what I have given you earlier, they are all there, and there is one beta, this is the alkyl substitute. If I take this double bond, single bond, double bond, single bond. So, this is alpha, beta, gamma, delta. So, this is the functional group. So, from the functional group you say this is alpha, this is beta, this is gamma, this is delta. So, there is one beta alkyl substituent, and for this there is one substituent here and another substituent here. There are 2 this is alpha, beta, gamma, and the gamma carbon atom there are 2 residues. So, each gamma contributes about 18 nanometers, that makes it 30. Extended double bond is the one extended double bond is the another addition of 30 nanometers, and then exocyclic double bond. Which one is that? This double bond is exocyclic to this 5 membered ring. It is attached outside immediately through a one of the corner carbon atoms. So, that is the exocyclic double bond. Lambda max expected is 285 and observed is 287 nanometers. Again see the closeness of the expected and calculated peak. Now, look at another example. This is parachloroacetophenone. This is a benzene ring. Okay. So, but there is a COCH3, C double bond O, 1, 2 double bond, single bond, single bond and double bond. So, parent value is 246 and there is a chlorine at the para position. So, expected is 10. If you look at the table, you will see that the observed value would be 256. Calculated value is 256 and the observed value is 254 nanometer within the experimental error. Now, another example, this is 3,4-dihydroxy acetophenone, again a similar structure what we had drawn, but it is in ethanol. So, the structure is this benzene ring COCH3 group 3,4-dihydroxy with respect to this COH3 1, 2, 3, this is 3 and this is 4. So, there are 2 hydroxyl groups on this structure. So, base value is again 246, meta hydroxy is approximately 7, and then para hydroxy is 25, calculated is 278 and observed is 281 nanometer. Beautiful, is not it? So, this is the speciality of the Woodward-Fieser rules. This I had already covered in the last class. So, we can draw an information about U visible. So, absence of peaks eliminates a large number of functional groups. Suppose you would see very less number of peaks, then you can say that okay, there are not many functional groups in this compound. So, if there are peaks, then you can say between, let us say between 180 and 300. If you see number of peaks, you can always say yeah, it could be an aromatic structure or it may not be an aromatic structure. If you see only 1 or 2 peaks, how many peaks do we expect normally? Sigma to sigma star, sigma to n to sigma star, pi to pi star, n to pi star, only 4 peaks. So, if there are no peaks like that, then we can say that it could be something like a hydrocarbon or something like that. So, we can always conclude that from the absence of peaks, we always say that yeah, so many functional groups are not there. Then if the spectrum indicates the absence of peaks, elimination of large number of functional groups is possible. It follows, is not it? So, then if there are some peaks, then we say that okay, there is a chromophore and the chromophore means it has to give some sort of a peak in UV and visible region. Now, you can say that you can match them with standard compounds, compilations, and there are number of compendiums available for number of organic compounds. The peaks have been recorded, and if the peaks match simply with respect to wavelength and intensity, you can say that okay, this peak has been matched in such a compound. So, the unknown compound what we are dealing with could be this compound. Therefore, we can always say by comparison of the spectrum, we can always say yes, this can be done. I can simply confer or reject the presence of a particular compound just by looking at the spectrum, U visible spectrum. Okay. So, resolution of sometimes cis transfer for isomers also is possible. This also I have covered a little bit in the last class. So, sometimes what happens is a charge transfer complex, it means some part of the some electrons of a functional group are transferred to a parent molecule, parent group, or to a metal atom, etc. And then some certain amount of transition takes place, but it is not an allowed transition. It need not be referred to sigma star or n to pi star, pi to pi star, etc. So, such a compound it forms a colored compound, not exactly known as a transition compound, that is electronic excitation, but some amount of an electron acceptor would be there. So, when an electron acceptor is there, the compound could be colored to some extent. So, such a compound is known as charge transfer complex. So, the charge transfer complex normally is colored. So, there is a donor atom, donor functional group, and there is an acceptor functional group. So, what happens here is when the product absorbs radiation, that is if I allow the light to fall on the material, then only the transition takes place. So, the compound becomes colored only when the electrons are transferred. So, it may be just routine regular sunlight, or it may be specific wavelength radiation also. So, this situation is somewhat akin to an internal redox process, because basically an electron transfer means reduction or oxygen. So, there has to be one receptor and there has to be one acceptor. So, basically it is a redox transfer. So, charge transfer bands normally it shows a peak. Okay. So, the peak corresponds to very high molar absorptivity. You remember I had discussed that absorbance is equal to epsilon Bc. So, epsilon represents the molar absorptivity. So, most of the charge transfer complexes have high molar absorptivities. So, the complexes generally absorb at higher wavelengths, that is lower energy, and this higher wavelength can quite often extend into visible range. That means, with an ordinary spectrophotometer you can see the charge transfer complexes displaying color can be determined by spectrophotometry. So, a visible range varies from 350 to 800 nanometers. So, you can, if there is a peak, if it is colored and like any rainbow, any of the rainbow colors you can visually see that. So, charge transfer complexes form an important part of spectrophotometry, because many of the inorganic metals and anions form charge transfer complexes with variety of organic compounds. So, that itself is a big part of a research which has been going on since 1920s or 1930s, and you can see that a large number of publications have been done, published on charge transfer complex determination of the metals and anions. Okay. Now, here are some well known charge transfer complexes. What are they? For example, if you take benzene, add a little bit of iodine to that, you will see a violet color, and this violet color colored substance solution exhibits a lambda max around 300 nanometers. That means it is colored. So, similarly, you take aniline, add tetracyanoethylene compound, you will see 3 peaks, one at 280, one at 300 and one at 610. Remember, the charge transfer complexes are not electronic transitions. It is only it is a big molecule in which charge is concentrating on one side of the molecule, giving rise to an impression of color compound being formed. But nevertheless, the charge transfer complexes can be used for spectrophotometry. Naphthalene picric acid is another one, and then there are several inorganic metals reacting with ligands. For example, this ferric iron reacts with thiocyanate to give you ferric thiocyanate, and ferrous ion will react with orthophenanthroline to give you another charge transfer complex. Iodine, if you add iodine to iodide solution, that also will give you a colored solution, that is also a charged complex, charge transfer complex. And fourth example or fifth example what I am giving you is quinhydrone and hydroquinone. This is a yellow colored substance which is in equilibrium with each other. So, in charge transfer complexes involving metal ions and a ligand, the metal serves as an electron acceptor. This is a very simple rule, because most of the metals are known as Lewis acids. Lewis acids have the property of acting as electron deficient compounds. So, any electron cloud coming near the metal, it tries to attract. So, the Lewis acid is a very simple known definition. Now, what I want to tell you is about the application. So, of this UV visible spectrophotometry. Now, I have told you that several organic compounds exhibit n to pi star, sigma to sigma star, pi to pi star and n to pi star transitions. Then charge transfer complexes can form with any of the organic and inorganic complexes. Therefore, the greatest applications of ultraviolet and visible spectrophotometry are in the quantitative analysis of organic, inorganic and biochemical compounds. Why? Because I can either form a specific compound or a charge transfer compound, and these are amenable to by Beer-Lambert's law, that is molar absorptivity is equal to A is equal to epsilon Bc, which is proportional to concentration. Therefore, it follows that the concentration of a substance is proportional to its molar absorptivity or absorption. So, inorganic compounds by themselves do not may not have chromophore. What metal ion will have chromophore? Nothing. It is just an ion, iron in solution, zinc in solution, they are all colorless basically. Maybe some of them are colored like chromium etc., but not all. 90% of inorganic ions are colorless. So, but they can undergo a whole gamut of chemical reactions which will give you colored complexes or colored anions and colored charge transfer complexes. All these can be employed in spectrophotometry. So, the applications of UV visible spectrophotometry, especially with respect to pollution control, normally involves determination of inorganic compounds, determination of organic compounds, determination of biochemical compounds, because quite often we always talk of E. coli and several other pathogens which are involved in these things. Okay. So, the applications are always like this, and then almost all elements of the periodic table except radioactive element can be determined in this way. Almost every element in the periodic table may be even sometimes we assume that sodium, potassium etc., they are all colorless, but still there are organic reagents which will give colored complexes with sodium and potassium also. So, many of them can be determined by spectrophotometry, but what happens is except radioactive compounds, normally we do not handle radioactive compounds in day to day analysis, nor do they enter our environment in discernible concentrations. So, some ions like manganese, potassium permanganate, that is MnO4, what I have shown you here, and dichromate, potassium dichromate, the anion is Cr2O7 minus. These such example, these are all colored substances, but they are all charge transfer complexes. So, most of the charge transfer complexes have incomplete d and f electrons. Apart from such cases, redox reactions, several other kinds of reactions can produce a colored product, or they can reduce the color by forming a non-colored product. So, all such things can be used in spectrophotometric analysis. Now, what type of reactions we can follow using spectrophotometry? One is catalytic reactions. Number 2 is determination of stoichiometry. I can find out if there is a colored compound being formed in a chemical reaction. I can always say that you can determine the composition, how much of the metal is there, how much of the organic compound is there. Sometimes it is very important for us to determine the stoichiometry of a chemical reaction. Sometimes these reactions can proceed in a rate determining step involving several steps. Therefore, it is also possible for us to determine the kinetic reaction rate, that also we can monitor. Then biochemical and enzymatic reactions, I have already explained to you that these things are important in day to day life, and diagnostic analysis in clinical chemistry and pollution control and in several other organic and inorganic reactions are possible, and that is the beauty of spectrophotometry. So, chemical reactions basically play an important role in the analysis of inorganic compounds. So, only thing is we need to have a proper choice of a chemical reaction and optimize the reaction conditions. What are the parameters? One is pH, another is reagent concentration, reaction time I have to optimize, temperature, order of mixing, stability of the complex, effect of other matrix components, ionic strength, statistical evaluation of data are required to establish a standard spectrophotometric method. So, once a method is standardized, the spectrophotometry provides an easy, sensitive, rapid and cost effective method to determine minute quantities of substances in microgram or sub-microgram levels. Further improvements we can always bring by solvent extraction, chromatographic separation and host of other related techniques, which are the tricks of the trade as far as a chemist is concerned. So, we will continue our discussion on the theory of spectrophotometry in the next module. Thank you very much.